I can. Sorry. Yeah, I hope I can cover the principles in this direction and also point out one or two like method and ideas along this direction and inspire some interesting thoughts and nice future works from every one of you. Let's move on. So basically, we know that machine learning currently has been ubiquitous in the world. It has been applied to different domains to make our life better. For instance, autonomous driving, intelligent medical treatment, smart city, etc. And also in many like security critical domains, for example, malware classification or fraud detection, those applications that will actually protect both personal and business information are also like well applied different types of machine learning techniques. But as we know that even such very powerful machine learning or AI techniques has brought us a lot of convenience. Currently, it also, on the other side of the coin, has brought us a lot of security and privacy concerns as well. For example, in 2016, the White House Associated Press Twitter account was hacked with phishing emails and spreading the rumor that the White House has been attacked, and which triggered the autonomous trading bot to dump a large amount of stocks within seconds and sweep about $136 billion within seconds, which is a real-world adversarial case and happens like generate severe consequences. And similarly, from the privacy perspective, for example, in the Australia airports, the biometric recognition systems have been developed for safety screening, which has raised a lot of privacy concerns as well. For example, if the database is leaked or if there are like models that can be reverse engineered to infer the training data, which contains a lot of privacy sensitive information, that's actually a big concern for everyone. So that is to say, in our current life, we have a lot of convenient platforms for developing and testing different types of machine learning algorithms and tools. For example, TensorFlow, Spark, etc. But we are still living in a very adversarial environment. In the real world, machine learners still actually have a very hard life to develop the so-called trustworthy machine learning or robust machine learning. And therefore, we have to first try to understand what the adversary can do and what's their abilities and constraints and goals, etc. And therefore, we can develop the secure or robust machine learning algorithms against the potential adversarial behaviors. So this is the whole like goal of the trustworthy machine learning. But then at this time point, maybe someone will ask, like, what is exactly adversarial machine learning, or what's the fundamental causal information, or what's the fundamental problem that we are trying to address? And on the very high level, intuitively, we can see that in traditional machine learning paradigms, right, we usually assume that the training and testing data are drawn from similar or even the same distribution. That's why we can train on one distribution and make inference on the other. But in the adversarial environment, consider the different like malicious behaviors. We can see either the training data distribution can be manipulated such that usually such attack is called poisoning attack, meaning that you can manipulate the training data and therefore the model trained on such data set will be so-called poisoned. And this is very practical actually. For example, if you have, the Netflix rating or Yelp rating system or even Twitter or etc., you can create a fake account and upload or comment on whatever poisoning messages or ratings, and you can actually mislead the recommendation or any types of trained machine learning systems. And this is usually called poisoning attack. And similarly, during the testing time, it's also possible that people can manipulate the test data distribution and generate the so-called evasion attacks, which means even like we can guarantee we train a model on vanilla benign data, we cannot guarantee in real, like the physical world, the test data is out of our control, right? For example, if it's a malware detection, then the adversary can generate or tweak the malware and try to bypass the malware detection systems. And such attacks can be very realistic and cause a lot of severe consequences. And in this talk, I will mainly focus on the test time attacks, which is called evasion attacks. But there are a lot of interesting like a training time attack or defense method, which if you are interested, we can also discuss briefly in the QA section. But we will focus on the test time attack first. And with that fundamental information and causality and like causal relationship, right? Basically the distribution shift. Then in our lab, which is called the Secure Learning Lab, we try to focus on design and certify the robust, private, and explainable machine learning pipeline. So what does that mean, right? Given this traditional, like say, direct machine learning pipeline, which involve input data and to the end of the final prediction. And in the middle, you may have some pre-processing like feature extractor, data cleaning, etc. And then you feed the data to train or optimize or fit machine learning model from the hypothesis space. And then you have some post-processing, for example, aggregation, different types of protocols to generate the final prediction, right? And along this standard pipeline, the first couple of things is we can first design different adversarial attacks, either training or testing time, right? So that we can identify the potential vulnerabilities of the existing machine learning model or pipeline. And then the next goal is to, of course, based on the vulnerabilities we identified, we will try to improve the robustness by designing, for example, robust features, like certified robustness on the representation, data, or model level, and give certain guarantees for robustness. And of course, based on this, we can also design different data valuation or based on information theoretical analysis to try to give certain model explanations so that when human look at it, we can understand the prediction made by the machine learning model. So we can more trust the machine learning model's prediction. And on the other hand, we want to protect the privacy of the along the whole pipeline. So we can use these types of similar information theoretical analysis or like robust feature engineering properties or generative models to protect privacy when we want train a machine learning model. So I would say these four mainly components form some foundation of trustworthy machine learning. And of course, among each component, there are multiple, actually many work along the direction, and we can pick some of them. But I hope you can, on the higher level, to get a big picture first. And among this, all the components in this talk, I'll mainly first talk about and give some like simple examples about adversarial attacks in physical world and see what's the potential attacks that could be and how we generate those attacks. And then we will mainly focus on how we can leverage the knowledge or inference or logic inference to improve the certified robustness of machine learning models against such adversarial attacks. And in the end of the talk, I may describe some principles about use game theoretical analysis to improve the robustness of machine learning models. But the second part will be the main component, and I think is actually quite novel currently. There is not a lot of work on it, and our group is focusing on it. So I think that may be a benefit that everyone can learn about it. Okay, so first let's look at some examples of adversarial attacks against the machine learning models so that we can have a flavor or a feeling about what adversarial attack means in a physical world. Right, so we all know that there are a lot of autonomous drivings. When we talk about AI or machine learning, maybe we think about autonomous driving, medical treatment, etc. And of course, in autonomous driving vehicle, there are a lot of sensors, right, like camera, lidar, radar, etc. So they have to, based on the models, make predictions and send the prediction to the control pipeline, and then make a decision for actions, etc. So that means if some of the sensors are attacked, right, by whatever it means, then it will be quite dangerous for the autonomous driving vehicles. And whether it is possible to attack such sensors, let me give some examples. So you can see here, these are two stop signs. They are actually the stop sign examples taken in real world. One is near Berkeley, one is in Vancouver, and one is Berkeley. So you can see in the real world stop sign, there are some graffitis and some patterns on the sign, etc., right? And that makes us think, what if these patterns could be adversarial, right? And for human, we cannot notice it because we see the pattern, but we think it's fine, right? We want to replace the sign. But if an autonomous driving vehicle coming through it and misrecognize this sign, for example, they will not stop, right? And this is quite dangerous. So let's see whether it is possible. So here is some interesting physical world challenges to generate such physical adversarial example of adversarial stop signs. So basically, compare with digital adversary attacks, there are some additional conditions or challenges. For example, in physical world, there are a lot of different physical conditions, right? For example, different angles and distances and lightnings. So it means if we add some perturbation to the sign, and if we change these physical conditions, the pixel values will be different, right? And then it make the attack more fragile. And also, I think maybe many of you have seen this example of adversary panda, right? You basically add the invisible perturbation to the panda. So as a human, you can see this is still a panda, but actually for machine learning model, it's misrecognized as a gibbon with very high confidence, right? But this means we can add a small magnitude perturbation to the panda, and so we cannot visualize the perturbation. But in physical world, we cannot add such perturbation as with small magnitude, right? Otherwise, the LiDAR or the cameras cannot see it. How can we address this problem, right? And also in physical world, there are some fabrication errors as always. So you want something to be red, but once you get it in physical world, it may print out or show up as green or pink or orange like that. And in the end, if we have an image, we can attack it, then we can add perturbation to the whole image, including the background everywhere, right? But in physical world, we only have the object itself. How could we guarantee that the perturbation will only be generated onto the object itself is another challenge. So there are many others, but these are some representative interesting challenges moving from digital world to physical world, right? And next, I will briefly introduce how we can address the challenges here, and we'll show some examples for physical attacks. So basically, in the digital world, let's quickly recap how to generate a perturbation to fool a machine learning model, right? Take the classification, supervised learning classification as an example, right? So in the traditional classification, what we have is this loss, like JF theta. Theta is a parameter of the model, give the X as input and the Y as the ground truth label, and we minimize this loss and to optimize the theta itself, right? And as an attacker, what we actually want to optimize the perturbation delta such that in this loss objective function, as an attacker, we want to minimize the magnitude of the delta such that it will be invisible for human, right? And the instance plus the delta, which is a perturbed instance, can go to the adversary target Y, right? So that you can fool this machine learning model. That's like a standard goal for adversaries in digital world, right? But of course, based on the challenges we mentioned before, how could we generate it to a physical world? There are some challenges. Regarding the first challenge about different types of physical conditions, right? So basically here, with the input X, we want to say, make sure the delta itself can be effective under different physical conditions, right? And in that way, what we can do is, instead of a single X, for each instance X, we can generate transformations. Basically, we sample a series of transformations, for example, different angles and distances, and add it to the loss function. So this loss function become a big expectation loss function, such that it is so-called kind of like a universal perturbation, so that this delta can be effective under different conditions for this xi, so that we can make sure this delta perturbation can be effective in physical world under different conditions. Right. And the second challenge is that we hope the perturbation itself is visible by the cameras, for example, right? But unnoticeable for human, right? And how do we do that? A direct way we can think of is we can generate a mask, right? Such that we mask out some regions so that the delta perturbation will only be optimized within this region rather than the whole space, right? And in this way, we actually can make sure the mask is of a meaningful shape so that it will not be noticeable for human. The human think it's a reasonable graffiti or something. So it will be actually called hiding the human psyche so that human cannot, identify it or notice it, but it can be visible patterns here. And of course, this mask is not arbitrarily generated. We can, in this loss function, we can first add L1 loss to it so that we can generate a sparse perturbation into the whole region. So you identify the vulnerable regions given the image, for example, right? And then you can replace this L1 with L2 inside or TV loss inside this region, such that this patterns in the region will be smoothed, and therefore you can identify the optimize the perturbation within this meaningful shape region. And after that, I will give a quick examples about the generated perturbation we can see. So basically, we can see all the stop signs on this slide are misrecognized as a speed limit sign 45. And the right turn sign is misrecognized as stop sign. So basically, this is a targeted attack, which is more severe, right? And you can see for different colors, it's a different types of attack. Like this is a subtle attack, which we look at it, it looks like just fading out, right? Similar here. And some are the graffitis with the letter love and hate, and some are just art with some white and black rectangles. So it's actually quite unbelievable that there's only the white and black rectangles here. For humans, it's still a quite reasonable stop sign, but for machine learning models, it can be misrecognized as a speed limit sign 45. And different row here shows different conditions like the distances and like the lightnings. So we can see they can consistently mislead the machine learning models. And this is a static analysis for the generated examples. And let me show some dynamic experiment. You can see on the left-hand side is actually one of the perturbed sign, stop sign. And on the right-hand side is a control experiment with a vanilla stop sign. And if you drive car towards it, you can see the caption consistently identify this sign as a speed limit sign, unless you go to very close to the sign itself. And this is just another example with the different types of adversarial perturbation. And you can see consistently this is misrecognized as a speed limit sign. So that means even you drive the car towards it with different angles and distances, it can be misrecognized as a speed limit sign 45. And that is for the classification model. And it is possible to use a similar optimization goal to attack the object detection as well. For example, this is against YOLO, and you can see the stop sign here can never be recognized, although all the other objects can be correctly recognized by this object detection model. And yeah, so this shows that different types of machine learning models can be attacked actually. And this is one of the example of white box attack, meaning that you have access to the stop sign, to the YOLO model itself. You can see even you get very close, you can recognize this stop, but we on purpose do not cover the letter here because that is meaningless, right? But it is too late for a car to stop here. And actually, some people ask a question about whether this white box attack can be generated to the black box attack, meaning we don't have any information about the target model, whether we can attack it. And one very interesting phenomenon in adversarial machine learning is called transferability, meaning that if you have an adversarial, say, instance, you can transfer it from model A to model B. So this is a quick example, which against the model fast RCN. So we use exactly the same, the perturbation or the stop sign we generated here, and test against fast RCN here. So you can see in the corridor, which is in a different environment, right? Still, the stop sign cannot be recognized unless you go to very, very close to it, which is too late for a car to stop. So that means for different types of models, like either white box or black box, it's actually very possible to generate the physical adversarial attacks against these models, even though there are several physical challenges against it. And this is very interesting that actually the Science Museum of London actually expedited this the adversarial stop sign in the museum, meaning that it actually can raise a lot of attention from different communities, and it's indeed a concern we should care about when we develop our machine learning models. So with these types of examples, I think people may ask the question that, okay, these are cameras, right? It's like a stop sign itself, although it's a physical object, it's a planar object. So what if we have the real, 3D object in physical world, and the say, given autonomous driving vehicle, there are different like LiDARs, radars, other types of sensors, right? So whether those sensors can be attacked or not. So I will not go to detail about this because I want to save some time for the defense, which I think is really the interesting part. But I want to show some example to give you the sense that indeed, not only like the planar stop sign, draw sign, but also the real world 3D object, etc., can also be attacked and very effectively. So for example, here we consider a LiDAR point clouds system, right? This is a very complicated pipeline of the Apollo open source autonomous driving platform. We don't need to pay attention to the detail to these slides. It's just to show you it's a disconnected component without an end-to-end differentiable model, right? But even though like this, we can still approximate or distillate this disconnected non-differentiable pipeline with a model, and then transfer that attack against the model to this pipeline and effectively attack such complicated real-world pipeline. So for example, we can generate a 3D real-world object and print out, like 3D print out it. And this is the one, maybe it's small, but when it gets closer, you will see. So we drive a car towards it, and this is like the LiDAR environment. So you can see if we drive the car towards this like adversarial object, actually it's a non-regular object. You can see the LiDAR here never identifies this object. When you get closer, you can see. So it's not very weird. It's just like a slightly irregular. But we put a box with similar size here to this part and test it as a control experiment. And you can see actually this is a green box, shows that the LiDAR can always identify this object. So that means we can actually generate a 3D object in physical world based on the optimization. Of course, here there are some additional challenge, meaning the object we need to optimize over 3D point clouds, and so that the 3D point clouds will have its own metrics, not LP norm, right? It's a chamfer distance, for example, so that we can make the object itself is still like not very obvious or weird to human visualization system, but still it can fool the system by clearly there is an object, but the LiDAR cannot detect it at all, right? And let me skip this example. But so actually this is a LiDAR system only. And after this paper, actually a lot of other papers show, in the autonomous driving vehicles, we not only have LiDAR or camera, we also have a sensor fusion system or all this like component together, whether it is possible to attack those sensor fusion systems, right? So a simple pipeline is, if you are interested, I will refer you to the paper later on, but this is actually a pipeline that you can consider different sensors, for example, into the whole pipeline and jointly optimize them and still make sure the object you optimized is quite of a meaningful shape, because this cone, we usually see such cone on highway, right? It's a very normal object on highway. So you can actually attack the whole sensor fusion systems, and we actually show that if you put this cone, like you can see this is a vanilla cone and this is a 3D printed out cone. And of course the shape is a little bit weird, but it's not that weird yet, right? And if we do the say simulation against it, against the different Apollo or LGSVL like simulation, you can see this is when like the adversary call. So you can see the car can never recognize this call. It can go past it, which is quite dangerous in practice, right? And in the control experiment, you can see the car actually stop at the call because it can recognize this object. So that means in the adversary environment, the object, even though it's a big object everyone can see, the autonomous driving vehicle system can never recognize it, which shows the vulnerability of current machine learning models. And yeah, there are a lot of other such examples online. If you are interested, you can play with. This is actually the 3D object we put on the road. And there is a link, and if you are interested, you can play with different examples. So actually, from the physical world perspective, right, these types of vulnerabilities we have shown to different companies, and there are many companies aware of that, and they are indeed trying to improve their models, which hopefully will have a safer autonomous driving vehicle systems later on, right? But so far, I hope all the examples are able to convince you that adversarial attacks are actually quite practical and can be generated actually easily, I would say, against the different types of machine learning models. So next, I would say, how can we defend against such adversarial behaviors, right? And consider that there are many papers from the defense side to defend against such adversarial behaviors, either defend or detect, right? And from different years, I summarize like there are some ensemble method, PCA, detection, or different things. But these types of work are based on the empirical perspective of defense. And I would say it's not robust enough yet, because usually this defense can be breached again by new types of attacks, which usually we call adaptive attacks, which means if you are a defender, I'm an attacker, and if you tell me what you are doing in terms of the defense, or if I can guess what you are doing in terms of defense, I definitely can attack your model again. It's kind of like a cat and mouse game, right? So definitely we need some theoretical guarantees of the robustness of the model, such that I can tell you with this guarantee, no future attack can attack my model anymore. Right. So if we can do this, that will be quite promising, right? And with that in mind, there is a long list of literature as well. Maybe it's too small, you cannot see clearly, but I just want to show you how much work in recent, 3 or 4 years, like people are focusing on these types of certification, meaning whether I can give you a certification for robustness, and usually such certification means a lower bound of accuracy. That means if I tell you the lower bound of the accuracy of the model is 90%, as long as your attack is within the constraint that I defined, then you cannot attack my model to be lower than 90% accuracy, which is a quite promising certification, right? So we don't need to worry about the future attack as long as those future attacks satisfy certain constraints, usually LP bounded norm for the perturbation magnitude. But of course, we can see in this certification, there are two big branches. One is deterministic approaches, which usually use some optimization-based tools to do the linear and nonlinear relaxation and solve LP optimization to give this lower bound, right? Or there is a probabilistic approach, which we can by sample to get sampling-based lower bound based on Neyman-Pearson statistical testing theorems, etc. But only this branch, probabilistic branch currently, can be scaled up to large scale, like a data set, for example, ImageNet. And this branch, because it's optimization based, it's very expensive to solve. So it's not scaled up to large scale data set. And even for the scale-up method, still, as we mentioned, the constraint for the attacks are still a little bit conservative, meaning we can only certify, say, LP bound within, say, 0.3 or 0.4. If it goes larger, the certification will give a very trivial bound, for example, 1% or even 0%. So there is still a big gap between the certified robustness and the empirical robustness, because we know on ImageNet we can even get 90 above percent accuracy, benign accuracy, right? But in terms of certification, now it's about 50 or even lower. So how we can fill in this gap, this is still a very active direction, and I think it's a very interesting direction. I hope if everyone interested, we can like definitely a very promising area we should focus on. But with this introduction about the existing like challenges, I would say, can we think about something else, right? So this is a main message I want to hopefully deliver in this talk. For example, currently we are always using optimization or sampling-based methods from pure data-driven perspective, right, to improve or certify the model robustness. Can we jump this out, like jump out from this like circle, right? Can we leverage additional information? Because as the stop sign or those example I show, you can see human cannot be attacked, right? Why? Can we leverage some knowledge from human or some logical inference from human? Because as a human, we know if it's a cat, we know it cannot swim, so it cannot in the sea. So we have such knowledge or logics, right? Can we incorporate such logics into machine learning models and make it robust? Which is a very challenging task, but maybe we can do something step by step, right? So here, I want to first introduce a framework, which is I call the sensing reasoning framework, which kind of can, I think, would be the first step towards this goal. But of course, there are a lot of improvement and things need to be done along this direction. For example, here, previously we always talk about a single neural network, right? For example, a single classifier, a statistical data-driven model, right, which can be attacked or vulnerable. Can we combine them into different neural network, and each of them try to identify different things? For example, this identify whether it is a dog, and this identify whether the input is an animal, right? And we connect with probabilistic graphical models, because in the probabilistic graphical models, they can make logical reasonings. For example, we can use Markov logic networks or Bayesian networks, and we have some factors to represent the logic. For example, this logic means that if the input is a dog, it's definitely an animal because a dog belongs to an animal, right? And if it's a stop sign, for example, it shouldn't be an animal because the sign is not an animal, right? So such logics, or even some arithmetic logics, or even some other logic knowledge we can think about. We can even extract some knowledge from an existing knowledge base, because there are many knowledge base, right? We can extract some rules, so that I would say this whole pipeline, I call it the sensing reasoning pipeline. So the sensing part is based on, say, statistical models like neural networks, and the reasoning part can be realized by different types of graphical models, and compose them so we have an end-to-end machine learning pipeline. We can certify the robustness of this end-to-end pipeline and see whether it is more robust, because it first takes the advantage of single neural network, like a good representation, universal representation, automatic scalable training recognition, right? But of course, this is vulnerable, as we can see. And then we can put it into the logical reasoning component, and so that we can use this to correct those mistakes made by the machine learning model at the sensing part, right? And so that we can improve the end-to-end robustness. So this is a high-level intuition, right? Hopefully from the end-to-end perspective, we can leverage the advantage of neural networks and leverage the reasoning inference, because this is very slow, right? And this doesn't give us good representation based on the traditional AI we know. So can we connect them and take the advantage of both types and make a certifiably robust machine learning pipeline? But of course, this pipeline, I think, makes sense, but there are several challenges about it. So first of all, let's see concretely what robustness guarantee means, right? So basically, we want to certify the marginal probability given the theta from alpha and alpha prime means the adversarial distribution, right? Whether we give the input to this end-to-end output, like this E theta means that if we get the marginal probability for the final prediction, this probability would be bounded by certain thing. So that's a certification we want. And there are some challenges. For example, we know with the probabilistic graphical models, the inference itself, for example, for MLN, is sharply complete, right? It's not linear and not polynomial, and it's very expensive. But that's not the end of the world, right? We also have some opportunities because the probabilistic graphical model, it have some good structures. We can actually leverage those structure because for neural network, we may lose some structures that can be understandable, right? We can leverage a structure from the probabilistic graphical models to do something and to solve the min-max problem, for example, to identify, to provide certain certification. So this is a simple realization of such sensor reasoning component. So basically we can see, give an input, we can have different sensors. The sensors are trying to identify whether this is a dog, whether it's a cat, animal, like that, right? And there are some factors, as we discussed, the cat belongs to an animal, dog belongs to an animal, right? And then there is a weight for each different factors. For example, for the edge factors, this is a logout. Basically, why the weight is like this? It's because if it's true dog, if that means the probability is 1, then this prediction for the dog is exactly the probability of the dog. And the other weights for the factors need to be trained. And based on this, we have different types of factors. And we actually, in the end of the day, our certification we want previously can be represented this way. So this actually is quite direct. We can take a brief look. So basically you can see for all the sensors here, they have different assignment, right? It's a dog, for example, dog is 1, non-dog is 0, they have 1, 0, and similarly for cat and animal. So you have all the possible word, right? Possible word means different assignment for these different sensors. And then we will calculate how many of this composition of those sensor assignment will give 1, meaning that it satisfies the logic here, right? Divided by all the a possible assignment, which is all the number of possible words. And then this probability actually would be the certification, right? Because you can see if this probability is high, it means that there are a lot of correct assignments, and it means we can certify the model correctly. Otherwise, the model is the whole end-to-end pipeline is wrong. So the goal in the end of the day is to calculate this probability of the correct possible word over all the number of all the possible words. And hope this is clear. And of course, even for this, this actually is quite a direct probability calculation. Even for this, it's slightly hard. And we can see the hardness is that this robustness that we want to certify, right? This robustness is actually can be reduced to a famous counting problem, which is a famous Champaign complete problem. And we can actually, by the way, prove that with the MLN model, this certification itself is Champaign complete, which is we don't need to go to detail about this, but what I want to show is that the problem itself is hard. However, there are very good tricks to solve this hard problem actually. So basically the goal is that what if we have some oracles for the inference of the say MLN, right? So basically you can see what we want before is to calculate the marginal probability, right? Which is we want to calculate Z1 minus Z2, and Z1 means the correct assignment and Z2 means all the possible word, right? And if instead of Z1, Z2, we have Z tilde 1, Z tilde 2 means this as the oracle. It means given the MLN program, I can tell you how many of them there are, right? I don't need you to solve it. Given this oracles, right? Actually, we find this problem becomes actually quite simple. For example, if we want to solve this, basically we want to solve this min-max problem, right? If we solve a min-max for neural network, it's non-convex and non-linear and we cannot solve it. But if we solve this min-max of this program, we find that we can prove that if there is a basically, Z tilde is a oracle we mentioned, right? And we assume this oracle equals to the true value plus some noise, right? Because the estimation or the oracle give you some randomness, right? And if the randomness lambda here, if it's positive, then this D is monotonically increasing. Otherwise, if it's like between less than 0, it will be monotonically decreasing. So it's always a monotone function. So you can see we can easily solve the min-max in the on the two points, right? And the C here is the magnitude of the perturbation. So we can exactly calculate with the minimal perturbation, which is minus C, and the larger perturbation with max C, what's the probability range. Then we can certify, okay, if I have a perturbation within this range, how likely what's the range of my output marginal probability is. I can certify this, right? That is great. But within a small range, from -1 to 0, it's not monotone, but we can actually show it's a convex function. So we can still use a first order method to solve it. So basically that means if we assume we have oracle, which is a noise estimation of the MLM program, we can actually easily solve this min-max problem. And this is a guarantee we can get. And the good thing is that this is a theoretical result, and we can see how we apply this to some empirical analysis, which I think is quite promising. For example, here is an image net, which my student called the primate net. So basically there are all types of primate, right? There's APA, great APA, and things. And there are two types of knowledge. One is the hierarchy. Basically, if you are for example, great APA, you belong to the APA category, right? This hierarchy. And this is an exclusive edge, meaning if you are APA, you cannot be this lemur, or if you are lemur, you cannot be monkey, right? You can only belong to one class. So it's exclusive. So basically you represent this knowledge as a first order logic, and you can implement this logic into an MLM program, for example, and then you can exactly build up the sensing reasoning pipeline we show. And even with such very simple knowledge, only two types of simple knowledge, you can see empirically, not only the benign accuracy, like robustness, we'll talk about it later, even benign accuracy is slightly improved with such knowledge, because we know always there is a trade-off between benign accuracy and robustness, right? But you can see with additional knowledge, rather than pure data-driven learning process, you can actually have higher benign accuracy even, like slightly higher than without knowledge, like a single end-to-end neural network, right? And consider the certified robustness, you can see it's not only 1%, 2% improvement currently with all the methods we show in the slides, like the numerous certified method. Here with the additional information, which is knowledge, you can see the certified robustness improve from 50% to 80%, which is a quite significant improvement. And similarly for different types of smooth sigma. So sigma here means a smoothing parameter, which is I won't go to detail about it. Basically, without knowledge, this certification is obtained by a state-of-art certification method, which is called randomized smoothing. And the randomized smoothing itself have this need this parameter. So we evaluate under different such parameter how the result is between the result with and without knowledge, right? So you can just view this is different parameter for this without knowledge model. And you can see basically it shows in this monkey net, the knowledge not only help to correct the prediction to be the green part, which is correct classification, but also with high confidence. Y here shows the frequency, which means the high confidence, meaning that it always correct the prediction with very high confidence, actually. And this not only apply to images, but also to some NLP tasks, which I will not go to detail, but it's just to show that similarly, not only benign accuracy, but also certified robustness, it's significantly improved. And the knowledge used here is a stock market prediction, and the NLP is the news. So the knowledge is about if there's a sentence saying the company make profit, then the stock market should increase, and the price of increasing and decreasing should equal to the close price of the day, which is just a very simple two type of knowledge, right? And you can see it's already quite enough to improve the certified robustness of the model. And another, I want to give a quick example because I want to go back to the stop sign example we mentioned it before, and then we can start the QA section. So basically we can see the stop sign before, right? And the stop sign, physical stop sign actually raised a lot of attention, and many people try to defend against it. And I would say so far there's no good method to defend against it because you can always adaptively attack it again. And the one idea similar with the sensing reasoning pipeline we have before, this is also a sensing reasoning pipeline. I just want to show how generalizable such pipeline could be, right? Given a stop sign, you can train different sensors, and the sensor here actually not the cat and dog. It's about whether whether there is a stop pattern and what's the shape of the sign, right? So basically, you know, if you there are two types of knowledge. One is permissive knowledge, meaning if you have the stop pattern, you will definitely be a stop sign, right? As in first O, and the other direction is O in first S, meaning if you are a stop sign, you should be of octagon shape, otherwise it's wrong, right? So just a very simple two direction knowledge, and build up this this part, knowledge part can be the conditional random graph, right? And I will not go to the theoretical result, but I want to show some very interesting empirical result, is that you can see the x-axis here are 46 types of attacks, including LP bounded physical attack, which is what we showed before, the physical attack, and the common corruptions and transformations, all types of attacks you can think of, because the defense here is attack agnostic, right? You don't need to worry about, you are not doing adversarial training, etc. So it's quite attack agnostic. And you can see the bar here shows how much improvement of this pipeline compared with state of art. And you can see there are a lot of high bars, meaning among all the attacks, this pipeline actually help to improve the robustness dramatically. Yeah, I think this is the very important messages I want to show. And of course, based on our what we showed before, from the benign accuracy, we can also see this knowledge enhanced pipeline, which is compared with a single neural network main sensor, the benign accuracy also slightly improve a little bit. And the robustness, of course, improve a lot. And there are some just the result for, if you look at the green, it's improvement, and you can see this on the physical attack, like LP bounded attack, basically lots of green, and benign accuracy sometimes sacrifice a little bit, and common corruptions, and yeah, a lot of different types of attacks. So I would say, yeah, here I think I'm slightly out of the time, but we have 10 minutes for the QA session. So basically I want to show two main messages. One is security and privacy problem in machine learning model currently is very important, and there are a lot of work on it, but still there still need a lot of effort to enhance and improve along this direction. And to improve the robustness of machine learning models, there are a lot of empirical work which can be attacked again, and there are some theoretical certification which is a little bit limited in terms of the magnitude that we can certify. And there are some, the third type is a knowledge-enabled machine learning pipeline, or maybe other additional information we can leverage to improve the robustness of our machine learning model and give a good certification bound, which is quite promising and also challenging. So I think I give some like a very simple example here. Hope that those examples can inspire you for better work in the future. Yeah, thank you everyone. Happy to take questions.
Thank you so much, Dr. Bolli, for your inspiring sharing on the certified robustness. All the attendees, please feel free to post any questions in the Zoom chat and also on the Fuva platform. And right now, I have gathered some questions for Dr. Bolli. Just give me 1 second.
Sure, yeah.
One of the participants have asked on the platform, what is the state of our solution for the certified robustness and currently how good it is?
Yeah, very good question. Actually, I would recommend people to read a survey paper we have. This is a survey paper here. Let me actually try to send a link. So basically, let me find the link. So basically, the state of art, there are two big branch, the deterministic. There is the state of art for the deterministic. I think currently is a beta quorum, the linear bound propagation, which gives the certification from the layer by layer propagation. And the other branch is randomized smoothing, probabilistic. And all the work here actually is a generalization of the randomized smoothing approach. For example, they can add adversarial training, add a consistent regularizer, different things to improve. And I think so far the state of art is called Maser, which is adding the consistency loss to the model training so that they achieve a state of art certified robustness lower bound. However, indeed, there are a lot of limitations. For example, on ImageNet or even on CFAR, the certified robustness here currently is only, on CFAR, I think is best like 60 something percent, not higher than 70 yet. So there's a big gap between the certified robustness and binary accuracy of the model. So definitely we need further improvement against such certified robustness. Let me find a link. There's where is the link? So basically, we actually, one of my students actually, I have lots of, so let me do this. Maybe everyone can see easily. So in the blog, there is a leaderboard. So actually, in the end of the leaderboard, you can see this graph I show, like this one, and there is a survey paper for this graph to explain each method in detail. And there is actually my student implement, or actually either implement or use the open source library include all the certified robustness methods here. So if you want to work on this direction, you can easily compare with all the methods here, and all the results are shown here. You can see, I think the state of art is not higher than like 60% on CFAR yet or something. And you can see the epsilon is quite limited. It's only on 30.3, 0.4, no larger than 0.5, I think. Yeah. So I can send the link to the chart. If people are interested in it, I think this could be a good starting point for this line of work. Yeah.
Okay, thank you. Thank you so much. And we also have one question posted in the Zoom chat. Are there any new advancement in the sensors to better capture data in real world and improve the machine learning model?
You only in the sensor part, right? Yes, there are many. For example, I believe they are using self-supervised learning or using contrastive loss or using generative model from the sensor perspective to help the sensor to improve the robustness or better capture the model. But these are more on the statistical learning side. So that means if it's an empirical improvement, again, like we said, we can attack the model again, which is unfortunate. Let me think. For other advancement, for example, I think people from the physical perspective, for example, take the autonomous driving as an example, right? People try to position the sensors in different views, right? So hopefully that will better capture the real world data from different view and more robust. It helps, just like the paper, many paper here, I summarize some like multi-sensor or like a sensor viewpoint and helps, etc. But in the end of the day, I think if we have access or have certain access to the input and output of the model of the whole sensor pipeline, it's still possible to attack it. So it needs some guarantees to improve the certified robustness. Maybe we need to connect a reasoning component after the sensors, such that the reasoning can use our knowledge or logical inference ability to certify the end-to-end pipeline robustness. Yeah. Hope that answers the questions.
Okay, thank you so much. And we also have another question gathered from the final question. Since we are due to the time constraint, we are running out of time. Yeah.
Sure.
So one of the students on the platform is asking, since the domain knowledge seems to be very important to come up with this model, how is this domain knowledge actually constructed in the first place?
Yeah, that's a very good question, and it's indeed hard. I mean, one way is there are a lot of knowledge base, right, from NLP community. For example, they extract knowledge from Wikipedia, from image NLP, from image query, or even some human labeled knowledge. For example, in our group, we actually do a big project like gather all the papers about COVID, for example, and then we extract some knowledge about the COVID disease from the papers, because the papers are more or less trustworthy, right? So we can get the knowledge from there. There are different ways, but indeed we need some human labor to construct such knowledge and construct the logics. Like not as a neural network, we can give the input and it can learn a good representation for us. That's a downside, but the good side is that here we don't need the knowledge to cover everything if our goal is to improve the robustness. If if it is for purely prediction, then we need as much knowledge as possible. But if our goal is just to improve the robustness for the sensors, then it doesn't need, because I only need a couple of knowledge. As long as I break one of the rule, I will know you are wrong, because I don't need you to break all the rules. So that means we actually don't need a comprehensive knowledge here, and we need a subset of knowledge rules so that they can identify the vulnerabilities. That is actually the nice part. Hopefully can help the whole pipeline. Yeah.
I see. Then if that's the case, you will greatly simplify the construction or the requirement on the knowledge base.
Exactly. Yeah.
Okay. Thank you so much. I think we are ending this presentation now. Meanwhile, let me share my screen. So for the next, we will have a student speech, personalized federated learning, a combinationary approach, high entropy neural networks for reinforcement learning. So we encourage all the attendees to take note of the timing and the upcoming sessions. And for this session, we are ending now, so feel free to leave this Zoom chat.
Hi, Dr. Bowley. I am Alex, who is a co-chair for this conference. I just want to say thank you very much for taking the time and effort to come and join us today.
Thank you for organizing it.
You were actually referred to us by Professor Boan. I'm not sure if you know him.
Yeah, sure. We are very good friends. Yeah.
Oh, okay. I see. It was a great presentation. I enjoyed it. So thanks a lot for joining us today.
Yeah, thank you.
Yeah, I would also like to thank you a lot for joining us.
It's been an honor to have you with us today. I'm sure that all the attendees have had a very insightful discussion with you, and we saw that there were some interesting questions on the board. So hope you also had a good time presenting with us, and we hope to see you in the next conference.
Yeah, definitely. See you guys later.
Okay.
Yeah. Thank you.
Thank you so
Bye.
much, Doctor.
Thank you so much. Then with that, I will end this call. Okay.
Lunchtime.
End the recording.
Okay.
Oh yeah, end the recording.